sklearn Neural Network. Description: the Neural Network module in scikit-learn provides a set of tools for building and using feed-forward neural networks for classification and regression tasks. It offers implementations of the multi-layer perceptron (MLP) with different activation functions and optimization algorithms. Inputs: data: a 2D array representing the features of your dataset. Each row corresponds to a sample, and each column represents a feature. Labels: a 1D array containing the target values for each sample in the dataset. For classification problems, these labels are typically integers representing different classes. For regression problems, these labels are continuous values. Outputs: predictions: a 1D array containing the predicted target values for new data points. Model: a trained neural network model that can be used to make predictions on new data. Steps: data preparation: the input data needs to be pre-processed before feeding it to the neural network. This might involve scaling features, handling missing values, and encoding categorical variables. Model definition: you choose the architecture of the neural network, including the number of hidden layers, the number of neurons in each layer, and the activation function used in each layer. Model training: the neural network is trained using the provided data and labels. The training process involves adjusting the weights and biases of the network to minimize the error between the predicted and actual target values. Model evaluation: after training, the model is evaluated on a separate test set to assess its performance on unseen data. Metrics: accuracy: the proportion of correctly classified samples in a classification task. Precision: the proportion of correctly predicted positive samples among all samples predicted as positive. Recall: the proportion of correctly predicted positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Mean squared error MSE: the average squared difference between the predicted and actual target values in a regression task. Visualization plots: loss curve: a plot showing the training loss over time. This can help to assess the progress of the training process. Activation histograms: histograms showing the distribution of activation values in each layer of the network. This can help to understand the activation patterns within the network. Decision boundaries: visualizations of the decision boundaries learned by the network. Particularly helpful for classification tasks. Fine-tune parameters: hidden layer size: the number of neurons in each hidden layer. Activation function: the function used to introduce non-linearity in the network, such as ReLU, sigmoid, or tanh. Learning rate: the step size used during the optimization process. Number of epochs: the number of times the entire training dataset is used for training. Uncertainty methods: dropout: a regularization technique that randomly drops out units during training, leading to a more robust model with less overfitting. Monte Carlo dropout: a method for estimating uncertainty in predictions by performing multiple forward passes through the network with dropout enabled. Bayesian neural networks: a probabilistic approach to neural networks that explicitly accounts for uncertainty in the model parameters. Challenges and fixes. Challenge 1: overfitting: the model learns the training data too well and performs poorly on unseen data. Sample use case that resulted in challenge 1: training a neural network on a small data set with a complex architecture. Fixes to challenge 1. Regularization techniques: L1, L2 regularization or dropout to prevent overfitting. Data augmentation: creating more training data by applying transformations to the existing data. Early stopping: stopping the training process when the validation loss starts to increase. Challenge 2. Underfitting. The model does not learn the training data well and performs poorly on both training and unseen data. Sample use case that resulted in Challenge 2. Training a neural network with a simple architecture on a complex dataset. Fixes to Challenge 2. Increase model complexity. Add more hidden layers or neurons. Use more powerful activation functions. Tune the learning rate to allow the model to learn more effectively. Train for more epochs. Challenge 3. Vanishing. Exploding gradients. Gradients during backpropagation become too small or too large, hindering the training process. Sample use case that resulted in Challenge 3. Training a deep neural network with many layers. Fixes to Challenge 3. Use appropriate activation functions. ReLU can help to prevent vanishing gradients. Gradient clipping. Limiting the magnitude of gradients during backpropagation. Batch normalization. Normalizing the activations of each layer. Improving the stability of the training process. Challenge 4. Local minima. The optimization algorithm might get stuck in a local minimum, preventing the model from finding the optimal solution. Sample use case that resulted in Challenge 4. Using a gradient descent algorithm to optimize a model. Fixes to Challenge 4. Use different optimization algorithms. Stochastic gradient descent (SGD) with momentum. ADAM. RMS prop. Initialize weights randomly. Train with different random seeds to explore different parts of the parameter space. sklearn, Neural Network, Bernoulli RBM. Description. The Bernoulli Restricted Boltzmann Machine (RBM) is a generative stochastic neural network that learns a probability distribution over its inputs. It consists of two layers: a visible layer representing the input data and a hidden layer representing latent features. The RBM learns to reconstruct the input data by minimizing the difference between the input and the output of the model. The model is trained using contrastive divergence, which is an approximation of the gradient descent method. Inputs. X a 2D array of input data, where each row represents a data point. Y an optional 1D array of target labels. Outputs. H a 2D array of hidden layer activations. PH give NV a 2D array of probabilities of the hidden layer activations given the visible layer. Activations. Steps. Initialization. The model initializes the weights and biases randomly. Contrastive divergence. The model trains using contrastive divergence, which involves iteratively sampling from the data distribution and the model distribution. Gibbs sampling. The model uses Gibbs sampling to generate samples from the model distribution. Metrics. Reconstruction error measures the difference between the input data and the output of the model. Free energy measures the energy of the model. Visualization plots. Hidden layer activations visualizes the hidden layer activations for different input data points. Reconstructed data visualizes the reconstructed data generated by the model. Fine-tune parameters. Learning rate controls the step size of the gradient descent algorithm. N components. The number of hidden units. Batch size. The number of data points used in each training iteration. Epochs. The number of training epochs. Random state. The random seed used for initialization. Uncertainty methods. Dropout. Randomly drops out units during training to prevent overfitting. Bayesian inference uses a probabilistic approach to estimate the uncertainty in the model. Parameters. Challenges and fixes. Challenge 1. The model may overfit to the training data if the number of hidden units is too large. Sample use case that resulted in Challenge 1. The model was trained on a dataset with a large number of hidden units and achieved perfect performance on the training data, but failed to generalize to unseen data. Fixes to challenge 1. Reduce the number of hidden units. Use regularization techniques such as dropout. Use early stopping to prevent overfitting. Challenge 2. The model may be difficult to train if the learning rate is too high or too low. Sample use case that resulted in challenge 2. The model failed to converge when using a very high learning rate, and the training loss oscillated wildly. Fixes to challenge 2. Tune the learning rate carefully. Use a learning rate scheduler to gradually reduce the learning rate over time. Challenge 3. The model may not be able to learn complex patterns if the number of hidden units is too small. Sample use case that resulted in challenge 3. The model was unable to learn the underlying patterns in a dataset of handwritten digits, resulting in poor performance. Fixes to challenge 3. Increase the number of hidden units. Use a more complex architecture, such as a deep Boltzmann machine. Challenge 4. The model may be sensitive to the initial values of the weights and biases. Sample use case that resulted in challenge 4. The model converged to a local minimum, resulting in poor performance because of the poor initialization of weights and biases. Fixes to challenge 4. Use a good initialization technique, such as Xavier initialization. Train the model multiple times with different random seeds and select the model with the best performance. sklearn, Neural Network, MLP classifier. Description: the MLP classifier is a feed-forward artificial neural network and that uses backpropagation for training. It is used for classification tasks where the target variable is categorical. It consists of multiple layers of interconnected nodes, each layer performing a specific computation on the input data. Inputs: X, a 2D array of shape n samples. N features representing the input features for training or prediction. Each row corresponds to a sample and each column corresponds to a feature. Y, a 1D array of shape n samples, representing the target variable for training. Each element in the array represents the class label of the corresponding sample in X. Outputs: YPRED, a 1D array of shape n samples, representing the predicted class labels for the input samples. Probabilities: a 2D array of shape n samples. N classes representing the probabilities of each class for each sample. Steps: initialization: the network is initialized with random weights and biases. Forward propagation: the input data is passed through the network, with each layer performing a weighted sum of its inputs and applying an activation function. Backpropagation: the error between the predicted output and the actual target is calculated and propagated backwards through the network, updating the weights and biases to minimize the error. Training: the network is trained by iterating over the training data multiple times epochs, adjusting the weights and biases until a desired level of accuracy is achieved. Prediction: once trained, the network can be used to predict class labels for new input data. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly classified positive samples among all samples predicted as positive. Recall: the proportion of correctly classified positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Loss: a measure of the error between the predicted output and the actual target. Visualization plots: loss curve: a plot showing the evolution of the loss function over epochs during training. Confusion matrix: a table showing the number of samples classified correctly and incorrectly for each class. ROC curve: a plot showing the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters. Hidden layer sizes the number of nodes in each hidden layer. Activation. The activation function used in each layer. Common options include ReLU, tanh, and logistic. Solver. The optimization algorithm used for training. Options include LBFGS, SGD, and ADAM. Alpha. The L2 regularization parameter. Learning rate. The learning rate used in the optimization algorithm. Maxiter. The maximum number of iterations for training. Toll. The tolerance for the optimization algorithm. Uncertainty methods. Confidence scores. The probabilities of each class for each sample can be used to estimate a uncertainty in the prediction. Monte Carlo dropout. A technique that uses dropout during prediction to generate multiple predictions, which can be used to estimate the uncertainty. Challenges and fixes. Challenge 1. Overfitting. The model may perform very well on the training data but poorly on unseen data. Sample use case that resulted in Challenge 1. Training an MLP classifier on a small dataset with a large number of features, leading to a complex model that memorizes the training data. Fixes to Challenge 1. Reduce the model complexity by decreasing the number of hidden layers or nodes. Use regularization techniques such as L1 or L2 regularization to penalize complex models. Use dropout to randomly drop out neurons during training to prevent overfitting. Increase the size of the training dataset. Challenge 2. Underfitting. The model may not be able to learn the underlying patterns in the data, resulting in poor performance on both training and test data. Sample use case that resulted in Challenge 2. Training an MLP classifier with a small number of hidden layers or nodes, leading to a model that is too simple to capture the complexity of the data. Fixes to Challenge 2. Increase the model complexity by increasing the number of hidden layers or nodes. Try different activation functions. Use a different optimization algorithm. Adjust the learning rate. Challenge 3. Vanishing gradients. The gradients may become very small during backpropagation, preventing the model from learning effectively. Sample use case that resulted in Challenge 3. Using deep networks with sigmoid activation functions, leading to very small gradients due to the saturation of the sigmoid function. Fixes to Challenge 3. Use activation functions like ReLU that do not saturate as easily. Use batch normalization to rescale the activations and prevent gradients from vanishing. Use gradient clipping to prevent gradients from becoming too large. Challenge 4. Slow training. The training process may take a long time, especially for large datasets or complex models. Sample use case that resulted in Challenge 4. Training an MLP classifier with a large number of hidden layers or nodes on a large dataset. Fixes to Challenge 4. Use a faster optimization algorithm like ADAM. Use smaller batch sizes for training. Use a GPU to accelerate training. Challenge 5. Difficulty in selecting hyperparameters. There are many hyperparameters that need to be tuned to obtain optimal performance. Sample use case that resulted in Challenge 5. Choosing the optimal number of hidden layers and nodes. Activation function, optimization algorithm, learning rate, and other hyperparameters. Fixes to Challenge 5. Use grid search or random search to explore different hyperparameter combinations. Use early stopping to prevent overfitting. Use cross-validation to evaluate the performance of different hyperparameter combinations. sklearn, neural network, MLP regressor. Description. The MLP regressor is a feed-forward artificial neural network and that is used to predict continuous target variables. It is built upon the principles of multi-layer perceptrons MLP, where interconnected nodes neurons are arranged in layers. These layers include an input layer, one or more hidden layers, and an output layer. The MLP regressor leverages backpropagation, a gradient descent algorithm, to fine-tune the network's weights and biases during training, minimizing the error between predicted and actual target values. Inputs X. This is a 2D array representing the training data with features. Each row corresponds to a data point, and each column represents a feature. Y. This is a 1D array containing the target values corresponding to the features in X. The target values must be continuous for regression tasks. Outputs YPRED. A 1D array containing the predicted target values for the given input features. Model a trained MLP regressor object that can be used for further predictions. Steps. Data preprocessing. The input features are often scaled or normalized to improve training stability and performance. Network architecture design. This involves specifying the number of hidden layers, the number of neurons in each layer, and the activation functions used for each layer. Weight initialization. The weights connecting neurons are initialized randomly or with specific strategies to break symmetry and improve training. Forward propagation. Input features are fed through the network, and values are calculated at each neuron based on activation functions and weights. Backpropagation. The difference between predicted and actual target values is used to calculate an error gradient. This gradient is then backpropagated through the network, adjusting weights and biases to minimize the error. Training. The forward and backward propagation steps are repeated iteratively until a satisfactory level of convergence is achieved, meaning the model's performance on the training data stabilizes. Metrics. Mean squared error MSE. This metric calculates the average squared difference between predicted and actual values. Root mean squared error RMSE. This metric is the square root of the MSE, providing a measure of error in the same units as the target variable. R squared R2. This metric represents the proportion of variance in the target variable that is explained by the model. A higher R2 indicates better predictive power. Visualization plots. Learning curve. This plot shows the model's performance, e.g., MSE on both training and validation data as the number of training epochs increases. It helps assess overfitting or underfitting. Feature importance. This plot visualizes the importance of different features in predicting a target variable. It can identify features with the most significant impact. Fine-tune parameters. Hidden layer size is a tuple specifying the number of neurons in each hidden layer. Adjusting this parameter determines the network's complexity. Activation. The activation function applied to each hidden layer. Popular options include ReLU, TANH, and Logistic Solver. The optimization algorithm used for weight updates. Common options are LBFGS, SGD, and ADAM. Alpha regularization parameter to prevent overfitting. It controls the strength of the penalty applied to the weights. Learning rate. The step size used during gradient descent. This value influences how quickly the model learns. Batch size. The number of training samples used in each iteration of gradient descent. Uncertainty methods. Bayesian neural networks. These networks treat weights as probability distributions, allowing uncertainty estimates in predictions. Monte Carlo dropout during inference. This technique introduces dropout, randomly disabling neurons to generate multiple predictions, providing a measure of uncertainty. Challenges and fixes. Challenge 1. Overfitting. The model performs well on training data but poorly on unseen data. Sample use case. A model trained on a small dataset with complex patterns might overfit, learning the noise in the data rather than the underlying relationships. Fixes. Regularization. Alpha parameter. Adding a penalty to large weights discourages overly complex models. Early stopping. Monitoring performance on a validation set and stopping training when performance starts to degrade. Dropout. Randomly deactivating neurons during training to prevent co-adaptation of neurons. Challenge 2. Underfitting. The model performs poorly on both training and unseen data. Sample use case. A model with a simple architecture might struggle to capture complex relationships in the data. Fixes. Increasing network complexity. Adding more hidden layers or neurons to improve the model's capacity. Adjusting activation functions. Exploring different activation functions to better represent nonlinear relationships. Hyperparameter tuning. Experimenting with different values for learning rate, batch size, and other parameters to find optimal settings. Challenge 3. Slow training convergence. The model takes a long time to achieve satisfactory performance. Sample use case. A large dataset with many features or a complex network architecture can slow down training. Fixes. Feature selection. Reducing the number of features by selecting the most relevant ones for a task. Optimizing hyperparameters. Adjusting learning rate, batch size, and other parameters to improve convergence speed. Using efficient solvers. Choosing faster optimization algorithms like ADAM or SGD with momentum. Challenge 4. Vanishing. Exploding gradients. Gradients become very small or large during backpropagation, hindering learning. Sample use case. Deep networks with many layers can suffer from vanishing or exploding gradients, especially with certain activation functions. Fixes. Using appropriate activation functions. Choosing functions like ReLU that avoid saturation in certain ranges. Gradient clipping. Limiting the magnitude of gradients to prevent them from becoming too large. Weight initialization strategies. Employing techniques like Xavier or He initialization to improve gradient flow.